Welcome to Lecture 9. We are going to pick up where we dropped off, where we stopped at the end of Lecture 8, where we were applying the steps for drawing Lewis dot structures. We only did a couple of examples, I think it was 3, and we will do the rest of those examples. I hope you have your steps written on an index card, and get your periodic tables out, and let's go ahead and get started. All right. Scroll down here to the examples. And we did not do HF last time, so let's start off with that one. That's going to be a fairly easy one. All right, so HF is going to be our first. Step 1, count your valence electrons. So find hydrogen, it's in group 1, which means it has 1 valence electron. Fluorine's in group 7, so it has 7. So we have a total of 8 valence electrons in this molecule. Step 2, connect with dashes. Okay, having done that, hydrogen is happy with just these 2 electrons that are indicated by the single bonding dash. So again, one line drawn between 2 atoms indicates that they are sharing 2 electrons. Third step, give everyone 8 except for the exceptions, hydrogen being the notable one. Fluorine here wants 8 electrons and it only has 2 at the moment. Those 2 bonding electrons in the dash are the only ones that fluorine sees. So we need to give fluorine 3 sets of lone pairs so that fluorine will now have a total of 8. Step number 4, recount your valence electrons and see if you indeed have the total that you counted in step 1. 2, 4, 6, 8. And this simple 2-atom molecule is finished. All right, moving on to F2. All right, pause at any time and give this a try yourself. All right, counting valence electrons, 2 times 7 is 14. Connect the 2 atoms with a dash and then give everyone 8. Right now, each one of these fluorines sees 2. So I'm going to give each fluorine 6 more in order that each fluorine has 8 around it. Now remember from lecture 8, we are not micromanaging these 7 came from this fluorine and these 7 came from this fluorine. That is not in reality how it works. All right. Now count up your valence electrons to see if they, step 4, to see if they add up to that total. 2, 4, 6, 8, 10, 12, 14. And we have solved the puzzle. Lewis dot structures is like a puzzle. You have to use the pool available to you, the total number of valence electrons, and keep everyone happy with their 8 electrons except for hydrogen and boron. All right, O2. 2 times 6, oxygen is in group 6, so 12 valence electrons. Go ahead and connect with a dash. And then I like to do it exactly the way the steps are written, even though I know by doing this that I am going to have too many, because I just did one like that and it was 14 electrons. This is 12. Let me show you what students often do. They'll put the 12 around and then sit there and say, I'm done. But you're not done because these oxygens are not happy. Each one sees a total of 6 electrons. 2, 4, 6. So in order that you make them happy, I wrote the steps so that you start off like this. Then the next step 5, which we haven't used yet, says if you have too many and you have these elements and these elements only with each other, so any combination within this set of 5, they can share more than 2. You have to be fairly small in order to share more than 2. So what we're going to do is we're going to put another dash in between the 2 oxygens, so they're sharing 4. And then we're going to take away some lone pairs because these second row elements, 2, 4, 6, 8, 10, cannot have 10 electrons around them. They're too small. They don't have the d orbitals available to do what's called an expanded octet. We're going to get to that. That's the last step on the card. So the oxygen molecule does have a double bond. The two oxygens are sharing 4 electrons. Okay? Moving on to nitrogen, N2, the element nitrogen. Nitrogen is in group 5, and you have 2. So you have a total of 10. You see that we are decreasing by 2 each time here. So if I do exactly what the steps tell me and give everybody 8, yes, I will have 14. But then step 5 comes into play, and I do have one of those elements, okay, that can share more than 2. So I'm going to erase at least one set of lone pairs, put another dash in, and like oxygen, I now have 12, 2, 4, 6, 8, 10, 12. I can't have 12, I can only have 10 with these 2 atoms. So I am going to take 2 more lone pairs away, one from each, and do a triple bond. And indeed, nitrogen, the element, does share 6 electrons between the 2 nitrogen atoms, a very, very strong bond. Let's talk for a moment about the difference between singles, doubles, and triples. Singles, you are sharing 2, so you don't have to get that close to overlap enough and overlap your orbitals enough to share 2. In order to do a double bond, you've got to overlap 2 sets of orbitals, so it's going to be shorter, stronger but shorter. And then to overlap 3 sets of orbitals in order to share 6 is the shortest of all, and of course the strongest of all. All right, moving on to, and that's a negative charge there on the NO2. It's a little hard to see. So we haven't used that step 1B yet, where all you're going to do for the negative charge is add an extra valence electron because it's negative. Where positive, you should be subtracting. So counting up valence electrons, 5 plus 2 times 6 plus 1 for that charge. And that is 18 valence electrons. Okay. Put the leftmost element, the one you have fewest of, in the middle, surrounded by the other 2. Connect with dashes. Give everybody 8. So that oxygen needed 6 more to give a total of 8. This nitrogen currently has 4, so give it 4 more. And this oxygen needs 6 more as well. Counting 2, 4, 6, 8, 10, 12, 14, 16, 18, 20. I have too many. Step 5. I've got 2 elements out of this group that can share more than 2, so I'm going to put 1 double bond in. Okay. Now what students, like to do at this point is they like, oh well, if 1 double bond's good, maybe 2's even better. Well, let's do it and count our electrons. This one, 2, 4, 6, 8, 10, 12, 14, 16, 18. This one's good. This one, 2, 4, 6, 8, 10, 12, 14, 16. This molecule does not have 2 double bonds because I'm not accounting for the 18 electrons I need. So don't get too carried away. Oops. Oh, look at that, red. I'm going to have to use that. All right, let's erase. And let's do our last example, which is SBr6. I have lots of electrons. Okay, counting valence electrons, group 6 for sulfur, group 7 for bromine, and you have 6 of them. So that is a total of 48 electrons. Sulfur is going to go in the middle. We're going to connect it to the bromines with bonding dashes. And in doing so, we are automatically putting 12 electrons around sulfur. Now, we will get to examples later where you're going to have to add lone pairs to the central atom. This is step 6. If your central atom is 3rd row and below, sulfur's on the 3rd row, those elements in the 3rd row and below on the periodic table have d orbitals that can be used for bonding as well. Essentially, the whole 8 thing comes from the s and the p's. 1s, 3 p's is 4 orbitals for 8 electrons. You throw in some d orbitals and you can get that number of electrons around the central atom up to about 12. We're about to talk about shapes of molecules, and it's dictated by the fact that these dashes signify electrons, which are negatively charged. They don't want to be near one another. With 6 bonds around an atom, you're essentially, everything is about 90 degrees apart from one another. The electrons are 90 degrees apart from one another. That's about as close as you're going to be able to get these negatively charged things that repel. Now, sulfur's got a lot of electrons around it. That's okay. It's third row. Bromine atoms, however, only have 2 at the moment, so each of those needs a total of 6 more to give each bromine 8. And then we're going to count. Always pair up. Don't put singles unless you have an odd number of electrons. All right, when I'm counting, what I usually do is go 6 with lone pairs when you have all the way around like that. 6, 12, 18, 24, 28, 32, 34, 36, 38, 40. Well, I must have miscounted. 1, 2, 3. I got 6 bromines with 6 lone pair electrons each. That's 36, 38, 40, 42, 44, 46, 48. I think that was good. Okay, so we've got our correct number of electrons. This is the Lewis dot structure for sulfur hexabromide. We kind of stopped naming. This would be, well, one more thing on these ions. The correct way for doing an ion, back to the nitrite ion, is that you put a bracket around it and then put that charge on the outside. As far as naming the oxygen and the fluorine and the nitrogen, you could either call it just oxygen, fluorine, or nitrogen. You could call it dioxide or difluoride. Nobody does. And then hydrogen fluoride or hydrogen monofluoride. You will not see that written, though. Everyone just calls it hydrogen fluoride because they only form the one compound. The NO2 negative is the common name is the nitrite ion. You could call it nitrogen dioxide anion, but everybody calls it nitrite. Okay. Remember the polyatomic ions I talked about in the last lecture that you need to memorize. Hope you've made your index cards or pieces of paper for helping you do that. Speaking of naming, we're going to talk about naming acids, our first introduction to what an acid is, before we move into shapes of molecules. All right? So, what is an acid? It is a compound that has a hydrogen atom bonded to a highly electronegative atom. So it becomes a very polar bond. Hydrogen being kind of left out in the cold with a positive charge. Hydrogen can then be taken away by a molecule such as water, losing H pluses, which we call protons. Hydrogen with no electrons is called a proton because it is essentially just a proton, because the most common isotope of hydrogen has no neutrons. So hydrogen with a mass number of 1 has 1 proton and no neutrons. The atomic mass of hydrogen is very close to 1, which means that that isotope is the most abundant. All right, we have a couple of different kinds of acids. We have binary acids and we have oxyacids. Binary means 2 elements. The most common binary acids are those combined with the halogens or with sulfur. So when it's just 2 elements, we use this hydro prefix, and it ends in -ic. So HF is hydrofluoric, HBr is hydrobromic, HCl is hydrochloric, and H2S is hydrosulfuric. So the hydro prefix ending in -ic. All right. Oxyacids, and there are many of them, have a lot of oxygen, it's a very electronegative element, and therefore the hydrogen bonded to the oxygen, is very easily lost as that proton, as that H plus. So this is the way to think about oxyacids. Almost all of them come from or are named in according to a polyatomic ion. So you take a polyatomic ion such as sulfate, SO4, with a -2 charge. Well, if you put a couple of hydrogens with that, which have a plus charge, so essentially you're putting together hydrogen sulfate, okay? So how many H's do you need to balance out that -2? You need 2. These are each plus 1, okay? Well, when you take sulfate and make it into an acid, because this ended in 8, then the acid ends in ic. So it becomes sulfuric. Okay? Sulfite, SO3, with a -2 charge. How many hydrogens do we need? 2 again to balance it out. So when you make sulfite into an acid, the ite ending becomes an us acid. So sulfurous. Okay? So 8 becomes ic, and ite becomes us in the acid name. So here's another one. HNO3 comes from nitrate, which has a -1 charge, nitrate does. Put a hydrogen on to balance it out, and the nitrate becomes nitric acid. All right? So that's the most important thing to remember for the oxyacids, is that they generally come from polyatomic ions. Now, and that's how the endings work. There are a couple of series, especially with the halogens, where you have a halogen, oxygen, and hydrogen. It happens with bromine, it happens with chlorine, and iodine, where you have, instead of having 2 ions like nitrite and nitrate, which becomes nitrous and nitric acid, and so on, you actually have 4. Well, the same thing kind of applies. And as the more oxygens you put on, the more the lower ones are end in ite, and the higher ones, the ones with more oxygens, generally end in ate, the polyatomic ions. So this polyatomic ion right here is the hypochlorite ion. Well, when you make that into an acid, it becomes hypochlorous. So it's still an ite becoming a us. But we have to add on a prefix because of the fact we have more than 2 in this series. If we just had ClO2 and ClO3, which are the 2 in the middle, then it would just be chlorous acid for this one because it came from chlorite, and the other one would be chloric acid because it came from chloric acid because it came from chlorate. But because we have a couple of extras in the series, we have to put on a prefix for the additional ones. So the one that has less hydrogens than chlorite becomes hypochlorite and hypochlorous. The chlorite ion, ClO2, ite becomes us. 8 becomes ic. But then the one that's one more than that one more oxygen, instead of saying hyperchloric, we say perchloric. And therefore the ic becomes an 8 again. I'm sorry. 4 is the... I need to change this in the notes. This is wrong. Oops, sorry. Hold on. This should be chlorate, perchlorate ion. And the acid is perchloric. How long it's been wrong? Probably forever. All right, let's do this a little example to reinforce our naming of acids, and then we'll move into shapes of molecules. So much fun. All right, so the thing to think about here is, what is this? First of all, is this A, B? What we're supposed to identify is whether it's an oxyacid or a binary, And then if it's an oxyacid, what is the polyatomic ion it came from? And the name of the acid. So obviously A is an oxyacid since it has oxygen in it. And B and C, but not D. This came from your book. They always like to do a 3 and a 1. So this ion here, one of the ones you're supposed to know, is the carbonate ion. So carbonate becomes carbonic acid. Okay, so came from carbonate. All right. Oh, here's one you should add to your list. I always miss it. This is the acetate ion. It comes into play a lot. So add that to your list. C2H3O2 with a -1 charge is the acetate ion. All right. It becomes acetic acid, which is what vinegar is, or at least 5% acetic acid. Here is a polyatomic ion you're supposed to know. This is the phosphate ion. Made into an acid, the 8 becomes an ic, and this is phosphoric acid. All right. Our last one, D, is a binary, and it is therefore prefix of hydro, and then chlor for the chlorine, ic, ends in ic, hydrochloric acid. All right. You've got a few in your recitation to practice as well. All right, we are moving into shapes. Comes from the Lewis dot structure. So we're going to be looking at the central atom. Now this little acronym here stands for valence shell electron pair repulsion theory, or I like to call it the they do not like each other theory. So this is that idea that negatively charged things repel, and they're going to arrange themselves as far apart in space as possible. So we're going to be thinking a little bit three-dimensional, and we're going to be thinking about some geometry that you learned a long time ago. All right, so what you're always going to have is what is on the next page in the notes in color. Isn't it pretty? And I should have already given this to you at the Tuesday recitation before you watched this video, a copy of this. Now on my copy, and I will write on this as I go, are some additional things written in. So you'll see that as we go through the lecture. All right, let's scroll back up, talk a little bit more about what we're going to do with this. So we are going to draw the Lewis dots first, and then we're going to use this geometry sheet to predict the shape. And then after we get finished with that, we are going to then, in lecture 10, apply the idea of polarity to the molecules. So Lewis dot, shape, and polarity, I call it the whole enchilada. You're going to end up using the front and the back of your card. All right, so we're going to work through some examples, and as we work through those examples and consult the sheet, I am going to be making reference to the difference between electron pair geometry and molecular geometry. Okay, now let's just talk about this example and bring a little bit of vocab in. All right, so this is the carbon dioxide molecule. What's missing on the Lewis dot structure of the lone pairs that should be on the oxygens? But this is the Lewis dot structure for carbon dioxide. What we're going to be focusing on always in determining shape is the central atom only. So what we're going to be doing is we're going to be counting up the number of groups of electrons around the central atom. Now, double bonds still count, each of these double bonds still counts as one group because it's just a large group. In space, they are in the same place. So we are placing electrons in space, so double bonds still count as one group. So if I look at this central atom, there are two groups of electrons around the central atom. Okay? We have a fancy word for that. We call it the steric number. Steric meaning, it has a geometry meaning. The electron pair geometry for this, the steric number, is directly related to the electron pair geometry. Okay? The molecular geometry can be the same, and in this case it is. When I have a steric number of 2, which is what I have here, then the shape, that steric number of 2, and we'll consult the sheet in a moment and I'll show you what I'm talking about, it is linear. Okay? Anything in the steric number 2 group is going to have an electron pair geometry of linear. All right? Well, it just so happens that essentially in steric number 2 you can only have linear, so the molecular geometry and the electron pair geometry are the same. Okay? All right, so let's go down to the sheet and let me show you what I'm talking about a little bit more. And we're going to work through those examples that are listed right there. All right, so if I go to the sheet, what I have on this sheet are the different steric numbers. And I believe what is written on there, let's see, I have one right here. Yes. What I have written on the sheet that you have a copy of, it says, over here on the left, it says SN for steric number. Well, this is the steric number 2 row. This is the steric number 3 row. And I'll scroll down in a moment. Let's talk about that steric number 2. There are no other possibilities for arranging two things around a central atom, two groups. Now, groups can be either bonded bonds, so dashes, or they can be lone pairs. Okay? That's what this means, non-bonded electron pair. So in this colored picture, and on yours it's a little harder to see, the lone pairs are denoted by this little oval. All right? Well, for a steric number of 2, you really can only have 2 bonds. So the electron pair geometry and the molecular geometry are the same. Okay? If we move down here to the steric number 3 group, in this first example, and in fact everything on the left column on your sheet are what I call the pure geometries, and that is everything in this column, the electron pair geometry, is equal to the molecular. Everything in this column. Okay? In steric number 2, there are no possibilities. So anything that's linear, the electron pair and the molecular are going to be the same. I know you don't quite understand this yet, so just hold on another minute or so. In the steric number 3, I can have 3 bonds around the central atom, or I can have 2 bonds in a lone pair. They both have the same electron pair geometry. They both have a steric number of 3. Steric number 3, steric number of 3. So steric number tells you the electron pair geometry. This lone pair, and this is true for all lone pairs, take up more room. They are not being held in place per se by being shared between 2 atoms, so they kind of spread out. Well, that affects the geometry. It ends up pushing these 2 bonds a little closer. So in a sphere that you have a 3-dimensional sphere that you divide into 3 pieces, the 3 pieces should be 120 degrees apart from one another. Well, anytime you have a lone pair, almost every time, it is going to push the bonds closer. So this bond angle here is less than, got that wrong, is less than 120 degrees. Somewhere around, I think, oh, there it is, written on yours, it says 115 to 120. Well, it's probably more like 115 to 119. So, once again, both of these possibilities for a steric number 3 have the same electron pair geometry, but the molecular geometry is different. Here on the left column, this one, they're the same. The electron pair geometry and the molecular geometry are the same. Electron pair geometry is trigonal planar. Electron pair geometry for this one is also trigonal planar. This one, the molecular geometry is trigonal planar, But for this one, the molecular geometry is bent because of that lone pair taking up more room. So for this one, electron pair is not equal to the molecular. Everything in the left column, the electron pair, is the same as the molecular geometry because none of those have lone pairs. Okay? All right. Now, and then if you scroll down, to the higher geometries of 4, 5, and 6, the same kinds of ideas apply. So 4, 5, and 6, here, left column, everything in this row has an electron pair geometry that is tetrahedral. Everything that's steric number 4 has a tetrahedral electron pair geometry. If you have a steric number of 4 but 3 are bonds and 1 is a lone pair, your bond angles, first of all, are smaller, about 105 to 109 here. That's what I have written on yours, 105 to 109, because of that lone pair. And if you have 2 lone pairs, as in the case of water, then that angle is even smaller, about 100 to 104. Okay? So for these two, they have a tetrahedral electron pair because they have a steric number of 4. So tetrahedral electron pair, but the geometries, the molecular geometries, is trigonal pyramidal for this one and angular bent for this one. Same thing is true down here for steric numbers 5 and 6. Okay? All right, let's do some examples and use these ideas. Okay? So let's go up here. And what I'm going to do is I'm going to, give us some room, okay, for doing the Lewis dots and then talking about the geometry. Okay, so get that sheet out that I gave you that we've been talking about. All right, the first one is CO2, and we've just gone over that. Let's do believe that's, excuse me, NCl3. Let me just give it a little bit more. Oops, sorry, hold on. A little bit more magnification here. We can see those subscripts a little bit better, maybe. There we go. Oh, that's much better. Okay, so NCl3, let's walk through it. First of all, we're going to do the Lewis dot. So 5 plus, counting my valence electrons, 3 times 7 is 21. So that's 26 electrons. Okay, nitrogen in the middle. Oop, my bad. I knew that's what it had, so let me do it the right way. Connect with chlorines. Dashes. Connect the chlorines with dashes. Give everybody 8. Got a little ahead of myself. Each chlorine needs 6 more because they only had 2 with that dash. Now nitrogen has 2, 4, 6, so that's why it needs that lone pair. Okay? Now let's count and see if we have 26. 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26. We do have 26. So, shape. Focus on central atom only. The steric number here is 4. 3 bonds, 1 lone pair. So steric number is 4, which puts it in the tetrahedral electron pair geometry, if you look at your sheet. However, the molecular geometry is not tetrahedral because of that lone pair. So if we go to our sheet, and I'm going to lose this ink if I do that, so I'm going to let you look on the sheet instead. 3 bonds and 1 lone pair have a molecular geometry of trigonal pyramidal. Trigonal pyramidal molecular geometry. So essentially, if you have a lone pair, your electron pair geometry and your, if I spelled that right, let's see if I did, pyramidal, I did, okay. Molecular geometry. So if you have a lone pair, these two, the electron pair and the molecular, will not be the same. So it's in the tetrahedral family, so to speak, in the tetrahedral electron pair geometry group, but the molecular shape is trigonal pyramidal. All right, SiH4. Anytime you want to stop the video and try this on your own. 4 for silicon, 4 times 1 for hydrogen, so 8 altogether. Putting silicon, I'm going to do it right here, silicon in the middle, connecting with dashes. Hydrogens are fine. Silicon has 2, 4, 6, 8, so it's good. And that gives us the total number of valence electrons that we wanted. Once again, we have a steric number of 4. And because we have no lone pairs, my electron pair geometry is equal to my molecular, and it is going to be tetrahedral. It's shaped like a pyramid. Below here in the notes, I've got a couple of links that will give you some three-dimensional pictures that you can rotate and so on to get a better idea of what these shapes really do look like. All right, moving on. Let's do BrCl3. 7 for the bromine for valence electrons plus 3 times 7 for the chlorine, so a total of 28. Okay. Bromine's going to go in the middle. Connect with dashes. Okay. Give everyone 8. All right. Count those valence electrons, and you will see that they come up to 26. 6, 12, 18, 20, 22, 24, 26. I need 28. Step 6 on your card says if you have too few and your central atom is third row and below, which is the case for bromine, I can give this bromine atom 2 more electrons for that to get up to a total of 28. So, putting that extra pair of electrons changed my steric number from what would have been 4 to 5. So this has a steric number of 5. Okay, that puts it in the trigonal bipyramidal, triangular is what this one says. I've seen it say. We'll go with that. Triangular bipyramidal. And the best way to think about this shape is to think about it this way. In the middle, so here's your bromine. Around the bromine, there is, or the central atom, there is a flat triangle, a plane that is triangular shaped. And that's where 3 of the things are. There's another one above the plane of the triangle and another one below. So that's the best way to think about this shape. This particular molecule has a trigonal bipyramidal electron pair geometry because it's in the steric number 5 group, but it does not have the molecular geometry of that. If you look on your sheet, 2 lone pairs on the central atom make this a T-shaped molecule, and that is the molecular geometry. So the presence of those lone pairs changes the shape. The bond angles are 190, a 90 between these things here, the plane and the things above and below, and between the things in the triangular plane are 120. I haven't really drawn it to look like that. Now, what happens in steric numbers 5 and 6 is the lone pairs take up some different positions than you might predict. It's it's a little harder to understand, but you'll always have the sheet, except for the final exam. Okay, PCl5. Let's go ahead and work through that one, and I'm going to scroll, so it means we're going to lose what we've done. In fact, I think I'm just going to erase what we've done and use this space. So if you need to stop and copy, please do. I'm going to get me a big eraser, and we're just going to erase all this. All right, so our next example is PCl5. Okay, Lewis dot, 5 for phosphorus for group 5 on the periodic table, 5 times 7 for chlorine, so 40 electrons total. Phosphorus in the middle, connect to those chlorines. Now, let me just say something about why you see me doing it, and I know you'll see it in the book. Why do we draw some of these things at angles? That's because those of us who've been doing chemistry for a long time already have an idea of the shape, and often that is depicted in the Lewis dot structure. I am adding lone pairs to the chlorines because they all want their 8, and they only had 2 with the dash. Phosphorus has 10, and that's okay because it's a third row element. It can have more than 8. It has d orbitals available for bonding. All right, so let's count up our electrons. 6, 12, 18, 24, 30, 32, 34, 36, 38, 40. All right, so how many things around the central atom? 5 bonds, no lone pairs. So I know without looking at the sheet that because I have no lone pairs, the electron pair geometry is going to be equal to the molecular geometry. This is going to be an example from the far left column on the page. This is a steric number of 5, just like the previous example. So it's going to be trigonal, triangular, I'm just going to go with trigonal, trigonal bipyramidal. I've seen it written that way as well. Okay. Next, XeF4. All right, 8 for xenon. Yes, you can make a noble gas if you're big enough, like xenon, bond with fluorine, which is the most electronegative element on the table. 4 times 7 is 28, and 8 is 36. Right, putting xenon in the middle, connecting those 4 fluorines with dashes. Okay, xenon has its 8, but each of these fluorines wants more lone pairs. Okay, counting up, 6, 12, 18, 24, 26, 28, 30, 32. Now xenon is way below the third row, so I don't have enough. So I'm going to add 2 more sets of lone pairs to the xenon to give it a total steric number of 6. 6 groups of electrons, 4 bonds, and 2 lone pairs. Those lone pairs on the central atom tell me that my electron pair geometry is, and my molecular geometry, that is, are not going to be the same. The electron pair geometry is octahedral because it is in that row. Okay? Just like everything else with steric number of 6. The molecular geometry, if I look on my sheet, molecular geometry is square planar. So it's a flat square molecule. The 2 lone pairs, as shown on the sheet, actually poke up above and below the plane. All right, SO2. 6 plus 2 times 6. I have a total of 18 valence electrons. Sulfur in the middle, giving everybody, giving everybody lone pairs to bring them up to 8. So 1, 2, 3, 4, 5, 6, and then 7, 8 for that oxygen. This sulfur needs 2 lone pairs, and this oxygen needs 3 more. Now, Some of you might have put on the 18 and stopped, but then if you did, somebody's not happy. 2, 4, 6, 8, 10, 12, 14, 16, 18, 20. I do need to do a double bond, just one. But don't put on 18 and stop, because that won't be any more correct than if drawing it with 20. So again, we take one lone pair off of each atom that I am going to involve in the double bond. Okay, so now we have 2, 4, 6, 8, 10, 12, 14, 16, 18. All right, focusing on the central atom, I see three groups of electrons around it, so the steric number is 3. The electron pair and molecular geometry are not going to be the same. The electron pair geometry is trigonal planar, just like everything in that row. But the molecular geometry for this one, due to that lone pair, is what they call bent. Okay? Just have 3 more to go. Practicing our Lewis dots certainly as we go, and learning how to use the geometry sheet. In lecture 10, we'll add the last little piece of the puzzle to it, and that will finish us up with all of the naming, formula writing, and concepts about bonding that we are going to do in this course. All right, so I'm going to use the big eraser, and I'm going to erase all this so I can do those last 3 examples. I like the big eraser. It's kind of fun. All right, next is nitrate ion. Okay. And remember, this is step 1. We'll deal with that negative charge. So we have 5 plus 3 times 6 plus 1 for the charge. It gives us a total of 24. Putting nitrogen in the middle and connecting with single bonds, 3 oxygens. Give everyone 8. Okay. Now count them up. 6, 12, 18, 20, 22, 24, 26. Again, we have too many. Step 5 comes into play. Again, don't stop with 24. Somebody will not be happy if you do. And let's get rid of 1. Oh, still have the big eraser. All right, I'll have to redo a little bit there. It's okay. Dash nitrogen, dash oxygen. Okay, and we're going to do 2. We're going to share 4 there. More than 1 double bond will not be appropriate, and this is an excellent example for the last thing we have to talk about today, and that is resonance. But we'll wait till we get there. All right, so, to be most correct, this is an ion, so we should put the brackets around and put the negative sign on the outside. All right, shape. Focus on the central atom. 3 sets of electrons. The steric number is 3. Because there is no lone pair on the central atom, I know that my electron pair geometry and my molecular geometry are the same. It'll be one of the shapes. Well, the shape on the steric number 3 row all the way to the left, and that is trigonal planar or triangular planar. A flat triangle of a molecule. All right, SF4. Counting electrons. 28 and 6 is 34. sulfur in the middle. Connect the 4 fluorines with bonding dashes. Sulfur is fine. Give each fluorine some more, 6 more, because they only have 2 with the dash. Okay, now count. Everybody's happy. 6, 12, 18, 24, 26, 28, 30, 32. And too few. Central atom is third row, so we're going to give it one more pair of electrons to get our total of 34. Okay, adding that extra pair changed my steric number from 4 to 5. So steric number is 5. I know that my electron pair geometry and molecular will not be the same because of the lone pair. The electron pair geometry is trigonal or triangular bipyramidal. My molecular geometry, because of the lone pair, find it on the sheet, is seesaw. All right, IF5. Iodine in the middle, 5 fluorines around. Oops, skipped the step. I guess we could wait and connect them, but I'm going to do it in order. 7 plus 5 times 7, so 6 times 7, 42 electrons. Connect the 5 fluorines to the iodine. Yes, that will give iodine more than 8, but it's way below the third row, so it can. Give each fluorine some more to give it a total of 8. I want you to know that that cat has been fed, if you can hear her. She just wants, I've got the door shut while I'm doing the lecture, and she doesn't like it. All right, so we gave everyone 8. Now let's count up. 6, 12, 18, 24, and 6 is 30. 32, 34, 36, 38, 40. Too few. Iodine is way below the third row, so we're going to give it one more set to give us our 42. All right, changed my steric number from 5 before to now 6. And I have a lone pair on that central atom. So steric number is 6. I know that my molecular and electron pair will not be the same because of the lone pair. My electron pair geometry, like everything in this steric number, is octahedral. But my shape is, for my sheet, square pyramidal. So the molecular geometry is square pyramidal. All right, hopefully with this set of examples you have gotten this concept down. It's not hard once you have gotten the Lewis dot structure thing. All right, we're going to scroll, talk about a couple more things to finish this lecture up. All right, I think we've hit that couple of paragraphs there really hard, and like I said, there are a couple of websites there that can give you lots of, give you a little bit more idea of what these shapes look like. Okay, there's the shape sheet in color, and we'll come back to that. I will keep that in for lecture 10 because we're going to need it. Those no's and yeses are going to become apparent as to what they mean in lecture 10. Right, what if we have something that's a little bit more complicated than just, whoa, that needs a little because of the, I guess because of the making it larger. Let me drop that down a little bit. It kind of changed my, well, maybe not. I guess just bringing it into Word did that. My molecule's not quite lined up. These hydrogens, let's see if I can fix it, are supposed to be, yeah, there we go, on the carbon. There we go. All right, so what if we have molecules where you've got more than one central atom. Well, the same ideas apply. So if we look at this molecule here, each carbon atom has a steric number of 4. So I can talk about, the geometry for each of these central atoms. Because there are no lone pairs, the electron pair geometry, of course, with a steric number of 4, is tetrahedral for each of those central atoms, and so is the shape. All right, so for each carbon, for each carbon center. That's how an organic chemist would think about it. So you just look at each central atom separately. All right. All right, last topic, resonance. All right, resonance occurs when you have alternating single and double bonds. And what happens in reality is that those double bonds move, the second bond moves. Single bonds are pretty locked in place, but the second bond of a double bond can actually move if it has a place to move to. So we've already done the nitrate ion right here. We just did it. So what I want to do is just talk about that one, just draw the Lewis dot again real quick because we just did it. And then we're going to do these. Well, there it is as one of the examples. So we'll just go ahead and do the examples. Never mind. All right, so let me scroll so I can get down to have a little bit more room. And we'll do these last examples. So you got to start with the Lewis dot structure. For those of you going on to organic chemistry, I cannot emphasize enough how important Lewis dot structures are for understanding organic chemistry. All right. So we're going to do the chlorate ion first. That's on your list. Don't forget, add acetate. All right, so A, we're going to do the Lewis dot. So here we go. All right, so 7 plus 3 times 6 for the oxygen, plus 1 for the charge, add it up, 18 and 8 is 26. All right, go ahead and connect them with dashes. Now, I said that resonance involved double and single bonds that can move. Resonance does not occur with triples. I already know before I draw this molecule that we aren't going to have any resonance because chlorine is not one of the 5 elements that can double bond. But we'll go ahead and finish. There's its extra set of lone pairs. One set of lone pairs to give it its 8. Okay, so I've given everybody 8. Now I'm going to count up, see if I have 26. 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24. I think I missed. Oh, 22, 24, 26. So I have my 26, and I don't need to do a double bond. Chlorine couldn't have anyway. So this one is fine, and there is no resonance because I have no double bond. We'll go ahead and do the next one as well. See if, if indeed, ClO4, if we can get all of our electrons in and not have any double bonds, because you should not. Now, I have seen this molecule with double bonds, but chlorine really cannot double bond. So 7 plus 4 times 6 plus 1, so 24 and 8 is 32. Okay? So essentially 6 more than the last one because you have an extra oxygen. All right, remember, this is taking care of the charge. Oh, my bad. We should have put a brackets, or just pretend that included that lone pair there, around that and put the charge on the outside. Okay, chlorine in the middle. Connect the 4 oxygens with bonding dashes. Give everyone 8. Chlorine already has 8 with those 4 bonds. And count your electrons. 6, 12, 18, 24, 26, 28, 30, 32. This molecule is fine with single bonds. Now when you get to 131, they will talk about formal charges. We are not doing that in 100. This molecule has a lot of formal charge, but chlorine should not be able to double bond. Okay? I'm going to go ahead and scroll, and we're going to do the last two. Now on those last two molecules, I see nitrogen and sulfur, which are my two of my five that can share more than two. They can double bond. So we've already done the nitrate ion, so if you will allow, I'm going to go through that one kind of quickly. 5 for the nitrogen, 3 times 6 for the oxygen, plus 1 for the charge. 6 and 18 is 24. So what we found just a little while ago when we did the Lewis dot structure, that if I give everybody 8 single bonds, I ended up with 26. So we indeed are going to put a double bond in. Okay, so I have my 24. Now, because this double bond can be here, here, or here, it does exhibit resonance. And what it means is this. Well, first of all, we use like little double-sided arrows to show that double bond moving. And in fact, if you look at data, like electron diffraction data for this molecule, you will see, you can look at that kind of data and see how long the bonds are. And remember before I talked about singles being the longest, doubles in the middle, triples being the shortest? Well, what you see when you look at molecules that exhibit resonance is that there's not two singles and a double in terms of the length. In fact, it is 1.3 in terms of what's called bond order, because that double bond moves between the three positions. So one way to think about it is, okay, I've got 3 positions and a total of 4 bonds. Well, 4 divided by 3 is 1.3. And you see a bond length that is about 1 1/3 for this molecule. For all 3 of these bonds, they're exactly equal in length. And what that means is this double bond is rapidly moving from one position to another so that they are essentially equivalent. One other way that we show, and I should be putting the brackets around because this is an ion. All right, one other way to show resonance and to show this movement is to draw it like I'm about to draw it. So here are 3 resonant structures. Another way to draw it would be like this. You put the singles in, and then you show with a dash, okay, that smeared out, and really don't need to put the lone pairs on, that smeared out extra bond. All right? Okay. One more, SO3. Does it have a double bond? And if it does, it should give us resonance because it has more than one position. If you have a double bond and it has nowhere to move to, then you will not have resonance. You have to have a single bond that's equivalent in order for it to move in that position. All right, so I'm going to go ahead and I'm going to scroll. And I'm going to see if I can get that back. I did get it back. I'll scroll a little bit more. But that's probably going to mess me up. Well, all right, what I'd like to do is, I want to do the SO3. It just takes up too much room. Okay, it's going away. All right, SO3. Oops. Okay, 6 plus 3 times 6 equals 18 and 6, 24 electrons. Sulfur in the middle, no ion here, oxygen, oxygen, oxygen. If I give everybody 8, I'm telling you it's going to be 26. We'll go ahead and do it, because I don't want you to put on 24 and stop. 6, 12, 18, 20, 22, 24, 26. Okay, so yes, I do have to erase a lone pair off of each two of the atoms that are going to be involved in the double bond, and then put in the double bond. And yes, this molecule can exhibit resonance because this double bond can be here, or here, or here. And we would show that with our double-sided arrow and draw the different positions. We would change the number of lone pairs depending on how many bonds to oxygen. So that's another resonance structure. And then the third one is the other position, which is here. And then you can fill in lone pairs. All right, and in lecture 9, we are going to go back to these Lewis dots and shapes, and we're going to add on this idea of pulling the electronegativity difference to talk about polarity of molecules. And that will wrap us up for exam 2.